Let's compare base 10 metric prefixes with analogous binary prefixes. We will also examine the year 2038 problem. And we will explore the use of Chinese numerals, with a special focus on the Myriad scale. Let's begin with an observation. 2 to the power of 10 is 1024. 1024 is very close to 1000, which is 10 to the power of 3. The base 10 metric prefixes represent powers of 1000. Now, because of this approximate relationship, we can reuse this system. We can adapt the naming convention from the metric prefixes, and we can create binary prefixes. Now, these are not exactly equal, but they are approximately equal. So they give us a sense of the order of magnitude. Let's have a look at this sequence of names. N is a positive integer, ranging from 1 through to 10. N is going to be used as an exponent. So here we have 2 to the power of 10n. That is the same as 1024 to the power of n. So instead of dealing with powers of 1000, we're dealing with powers of 1024. For n equals 1, we have a name that is analogous to kilo. The prefix kilo means 1000. The prefix kibi, which is denoted by ki, means 1024. So we're going to use the same letters as the base 10 metric prefixes, but we're going to add a lowercase I to indicate that we're talking about a binary prefix, which is analogous to the base 10 metric prefix. So for n equals 1, kilo becomes kibi. For n equals 2, mega becomes mebi. For n equals 3, giga becomes gibi. For n equals 4, tera becomes tebi. For n equals 5, peta becomes pebi. For n equals 6, exa becomes xb. For n equals 7, zeta becomes zebi. For n equals 8, iota becomes yobi. For n equals 9, rona becomes robi. And for n equals 10, queta becomes quebi. So these are the 10 names that are used. So we can have a base 10 metric prefix, which is analogous to a binary prefix. Now let's pay special attention to n equals 3. So if we were using the base 10 metric prefix, this would be giga. Now giga is the same as a billion, which is 10 to the power of 9. And what about the analogous binary prefix? Well, it is gibi. Now that is 2 to the power of 30. So that means that 2 to the power of 30 is approximately a billion, or 10 to the power of 9. What about 2 to the power of 31? We just need to double it. So it is approximately 2 billion. And what about 2 to the power of 32? We can double again. So it is approximately 4 billion. Now, why am I specifically focusing on these values? It is because they are relevant for the year 2038 problem. Let's explore this problem. We need to introduce Unix time. Unix time is measured in seconds. And the 0 is set at the first second UTC of the year 1970. That's 1970. So at the beginning of this year, UTC, we start counting the first second. And then we count the next second. And we store that value as a 32-bit integer. So historically, this is the way it was done. So if we use a signed 32-bit integer, then we can store all the values in this interval. So for a signed 32-bit integer, we can store values from minus 2 to the power of 31 all the way to 1 less than 2 to the power of 31. So from 0 to this value over here, we have approximately 2 billion seconds. But the entire interval is approximately 4 billion seconds. So it's not exactly equal to 4 billion, but it is an approximation. So we have the correct order of magnitude. And that is actually why we're introducing these analogous prefixes, so we can get a sense of the order of magnitude. So we have roughly 4 billion seconds in this interval. Now that is a problem, because if we keep counting every second, and we update that signed 32-bit integer, eventually we're going to reach this value, which is 2 to the power of 31 minus 1. Now what happens when we reach this value and then we count up to the next second? That's going to take us back here to this value, to minus 2 to the power of 31. So that's a problem. Now we're back here in the year 1901, or 1901. That's going to cause lots of problems with timekeeping. So that is called an integer overflow. So we overflow and we go back over here, and that is because we're dealing with a signed 32-bit integer. What if we instead use an unsigned 32-bit integer? Then instead of this range, which includes negative values, we just have positive values over here. So 0 is the starting point, and then we go over here up to 1 less than 2 to the power of 32. So 2 to the power of 5, that is 32. So this value over here is approximately 4 billion. So we have this range over here. But that is just moving the problem forward. It's moving it into the year 2106. So instead of dealing with the issue in the year 2038, we deal with the issue in the year 2106. So what is the solution to this Y2K38 problem? Instead of using 32-bit integers to store the Unix time, we can use 64-bit integers. And then we have plenty of room to store all of the relevant values that we need. So this is an issue that arises from using 32-bit integers to store the number of seconds from this value over here that is set equal to 0. So that's when we start counting the seconds. And the naming convention Y2K38, that is analogous to the Y2K issue. And that is not an issue with binary notation. That is actually an issue with decimal notation. So the Y2K issue is similar to this issue, but instead of dealing with these binary values, we're dealing with 4 decimal digits. So to store a year, for example, the year 1901, you can represent this value using these 4 decimal digits. So we're dealing with base 10. But to save space, you can just use 2. So you can use 01 to represent the year 1901. And for 1970, you can just use these 2 digits over here. You can just use 70. But what happens if you're dealing with a time span that is larger than a century? Then you're going to have multiple years that are displayed using the same 2 values. So 01 could mean 1901, but it could also mean 2001. So there's an ambiguity there. So that is the Y2K problem. And it is closely related to this Y2K38 problem, because it's also about timekeeping. Where Y2K is concerned with years, Y2K38 is concerned with seconds. So these are all timekeeping issues. Now, the next thing that we need to discuss is, let's take a special look over here at n equals 5. So n equals 5, if we were dealing with the base 10 metric prefix, we would call this peta. But because we're dealing with the binary prefix, we're going to call this pebi. So pebi refers to 2 to the power of 50. So that is 10 times 5, 50 up here in the exponent. 2 to the power of 50 is approximately 10 to the power of 15. So this approximation is very important, and we're going to use this as an example. So up here, we have this example value. So this value that I've written up here, that is actually the same as the value that's represented by the prefix pebi. It is 2 to the power of 50. Now we can read this value as 1 quadrillion, 125 trillion, 899 billion, 906 million, 842,000, and 624. So notice how I'm grouping the digits into groups of 3s. So we're dealing with thousands. It's just like over here. We're dealing with thousands, and that is analogous to dealing with 1024. So we're dealing with values that are close to 10 to the power of 3. That is a natural way to group these numbers in English. But there is an alternative way. We could also use the myriad grouping. So instead of grouping the digits into groups of 3, we could group them into digits of groups of 4. And that is what is done with Chinese numerals. So now let's investigate Chinese numerals. And we're going to be using the myriad scale. So let's have a look at these characters which are used to describe powers of 10. So first we have the character for 10. It looks like a plus sign. So this is 10 to the power of 1. And the metric prefix is DA. So note that we're using 2 letters. We have lowercase d, lowercase a. Why don't we just use a single lowercase d? Well, it's because single lowercase d refers to deci. Deci refers to 10 to the minus 1. But over here, we're dealing with 10 to the plus 1. So this is called deca. So deca refers to 10. And here we have the Chinese character for 10. Next, let's have a look at 100, which is 10 to the power of 2. We have this Chinese character for 100, and we can also use the prefix hecto. So we have deca, hecto, and then for 1,000 we have kilo, and this is the Chinese character for 1,000. Observe that we're using a lowercase k over here for kilo. But over here we have an uppercase K for kibi. So we have uppercase K followed by I, and that distinguishes it from kilo. So we have kilo, and then this is kibi. And then for 10 to the power of 4, this is the same as 10,000, or a myriad. We have this character. So this is a simplified version, and this is a more complicated or traditional version, which has more strokes. Now, both of these characters represent a myriad, which is 10 to the power of 4. So this is very similar to the ancient Greek system. The ancient Greeks preferred to deal with myriads as well. Now, let's have a look at these powers of 10. Here we have 10 to the power of 5, 10 to the power of 6, 10 to the power of 7, and 10 to the power of 8. We can describe them as 10 myriads, 100 myriads, 1,000 myriads, and then a myriad myriads, which is a myriad squared. And then we can introduce a new character. This is the character for a myriad squared. We have a simplified version and a traditional version. You can see the traditional version has many more strokes than this simplified version. So myriad myriad can also be written like this. And I'll refer to this character as myriad squared. So it represents 10 to the power of 8. Now observe that 10 to the power of 6 is represented as 100 myriad. And this is equivalent to mega. So mega corresponds to n equals 2. And mega is analogous to mebi. So here we have mebi, and that is analogous to mega. Now, let's have a look at this column over here. So 10 to the power of 9 can be represented as 10 myriad squared. Or we can also represent it as giga. So over here we have giga. That corresponds to n equals 3. And giga is analogous to gibi. Now observe that there is also a Chinese character for giga. So this is the Chinese character that is used to translate this metric prefix giga. But we can also think of it as 10 times the myriad squared. Then for 10 to the power of 10, we have 100 myriad squared. For 10 to the power of 11, we have 1,000 myriad squared. And 10 to the power of 12, we can think of that as a myriad times myriad squared. Or we can write that as a myriad cubed. Now this character can be used to mean 10 to the power of 12, or a myriad cubed. But keep in mind that there is some ambiguity, because sometimes this character is used to represent mega. So it's used for 10 to the power of 6. So in other contexts, you might see this character put over here next to mega. But to avoid ambiguity, we can use 100 myriad to specify that we're dealing with 10 to the power of 6. So that is 1,000,000. And over here for 10 to the power of 12, to avoid ambiguity, we can use this character, which is a translation of tera. So we have tera, and you can see tera over here that corresponds to n equals 4. And tera is analogous to the binary version, which is tebi. So we have tera and tebi, and this is the Chinese character for tera. And finally, let's look at these 4 powers of 10. So we have 10 to the power of 13. We can write that as 10 myriad squared. And alternatively, we can write it as 10 myriad cubed. So we can read this as myriad cubed. Then for 10 to the power of 14, we have 100 myriad cubed. So here we have a myriad by itself and then myriad squared. And then for 10 to the 15, which is very relevant, it's important for our example over here. For 10 to the 15, we have 1,000 myriad cubed. But we can also use the label peta. So peta corresponds to n equals 5. And peta is analogous to pebi. That's the binary version. And peta can also be written with this Chinese character. So that is for 10 to the power of 15. And then finally, we're going to have a look at 10 to the power of 16, which can be thought of as myriad squared times myriad squared. And that is equivalent to myriad to the power of 4. So we have a myriad to the power of 4, and that is described by this character over here. And we're using the myriad scale, so this character represents 10 to the power of 16. So now that we have examined these characters, let's read this top line above the Hindu Arabic numeral representation. So we can start over here from the value that's next to 10 to the power of 15. So I'm going to read out these values. We have 1,100, 210, 5 myriad cubed, 8,900, 910, 9 myriad squared, 0, 600, 810, 4 myriad, 2,600, 210, 4. So we're grouping these digits into groups of 4. And we're dealing with myriads and powers of myriads. So instead of dealing with, over here we have a million, a billion, a trillion, and a quadrillion, we're dealing with a myriad over here. This is the myriad. And then we have a myriad squared, and then a myriad cubed. And if we kept going and we had 10 to the 16, then we could use this character over here, which is a myriad to the power of 4. So that's a very interesting way of expressing these numbers. So that is the convention if we use Chinese numerals. And something that is also very interesting, we can express this value using an alternative Chinese numeral system. This is called the Chinese rod numeral system. It is also a positional base 10 system. So beneath these Hindu Arabic numerals, we can see the rod numerals. Observe that 0 is represented by a blank space. So we don't need to use a character to represent 0, we can just have a blank space. And these were actually represented by physical rods. So that's why they look like rods being put on a flat surface. You can see that 4 is represented by 4 rods. 2 is represented by 2 rods. If we go above 5, then we can use a perpendicular rod to indicate that we are at 5, and then we can add the additional rods. So for example, 6 is a perpendicular rod, which indicates 5, plus 1. And another example, 8. 8 is a perpendicular rod, plus 3. That's 5 plus 3. And 9 is a perpendicular rod plus 4. So that is 5 plus 4. And observe that we're alternating between having vertical and horizontal rods. Now, why would we do that? Well, it's to avoid ambiguity. If you have two of these rods next to each other, and they're both representing 1, then if you move them slightly closer, then that can be misinterpreted as representing 2. So if we just rotate and leave a little space, then there is no ambiguity. So this 1 is definitely referring to a separate digit from this one over here. So that is a very useful convention. So you can see that alternation between vertical, horizontal, vertical, horizontal. So these are the rod numerals, and below them we can see the Suzhou numerals. And the Suzhou numerals were developed from these rod numerals. So instead of having physical rods on a flat surface, which is usually denoted with some grid lines, you can use these numerals, which are written. And you can see that 1 and 2 still look very similar, but there are some differences. So 8 still looks very similar. We still have a perpendicular line plus 3. And you can also see that there is 6 over here. 6 is represented by a perpendicular line with plus 1, so it's 5 plus 1. But 4 is not written as 4 separate strokes. Instead, it's written as 2 strokes. So we have 2 strokes, and that simplifies the character. So we have less strokes. So this X represents 4. And 9 can be represented as a perpendicular line and an X. So we have a 5 plus 4. And if you write that quickly, so you have a vertical line, and then you write the X, then it turns into this shape. So that's where this shape comes from. So you have a vertical line, and then you write the X. So that is 5 plus 4. And that is repeated 3 times over here. We have 9, 9, 9. And you can see we don't actually have to rotate because there's no ambiguity. And the only time we have to rotate is when there is an ambiguity, like for these values over here, for 1, 1, and 2. So here we rotate, we write this perpendicularly, so that this 1 and this 1 are treated as separate numerals. So that they're not confused for a 2. So that explains 9. What about 5? 5 can be thought of as a vertical line plus a loop. Now this loop represents 0. So we have 5 plus 0. So instead of writing 5 strokes, like we have up here, we can just write a perpendicular stroke, which indicates we have reached 5, and then we can write a loop to indicate 0. And if you write that quickly, you can see how this digit can emerge. So that explains both 5 and 9. So 5 is 5 plus 0, and 9 is 5 plus 4. And you can see that in these Suzhou numerals, there is a 0 included, and it is a circle. So instead of just using a blank space, you can use the circle to denote 0. So both the Suzhou numerals and the rod numerals are base 10 positional numeral systems. So in this video, we have explored Chinese numerals, we have used the Myriad scale, and we have explored a comparison of the base 10 metric prefixes and analogous binary prefixes. And we saw how that was related to the Y2K38 problem.